One of the weirdest things that we found from quantum mechanics is that if we have two objects, like two photons, and you pass them through neighboring slits, they're both going to act like waves and like particles, and those waves can actually interfere with each other. You can start having constructive and destructive interference between them. And that doesn't just happen with photons and light, but that can actually happen with matter as well. So I wanted us to get to see the deBroglie wavelength here. That's actually going to be the wavelength that matter has. Now, back then we mentioned that if you put an electron through a slit, the electron also had a wavelength to it, and you could have interference patterns emerge on the other side of the slits too. This is what the equation for that looks like. Our deBroglie wavelength, now keep in mind this is the deBroglie wavelength. This is not for photons. You can see deBroglie wavelength is going to equal Planck's constant divided by the mass of the object times its velocity. So we have a constant, and then we're going to have the wavelength get large when you have really small masses and really small velocities. If you have both of them small, then you're going to end up having a big wavelength. Now here's where things get pretty interesting with it. Let's take a look at a couple of different objects and see what sort of a wavelength they should have. Well, let's start out with a slow electron. So you see here the mass of the electron. Well, mass is small. If we were to somehow slow an electron all the way down to 1 meter per second, small velocity, small mass, I expect there to be a really big wavelength. And this number may not seem giant to you, but let me point out, this is meters. If we go down 3 orders of magnitude, we'd be in millimeters. So at that point, what we'd have is 0.7 millimeters. I'll point out, that's something you can see with your naked eye. Picture 1 millimeter on a ruler. Now just picture 3/4 of that. It's going to be something fairly small, but we're talking about something about the size of the tip of your pen. In fact, a lot of those ballpoint pens are going to be listed as 0.5 millimeter if you look on your pen cap. So we're talking about making the electron the size of the ball bearing at the end of a ballpoint pen. All you have to do is slow the thing down to 1 meter per second. But whenever we talk about the structure of a molecule or an atom, I like to constantly point out that the electron is moving at close to the speed of light. So let's go ahead and crank its speed back up. Now the speed of light is going to be more like times 10 to the 8th. So we're at, 1/100th the speed of light, something like that right here. Well, if we slow it down to that point, we're going to have a much, much smaller wavelength. Now this is going to be, notice, 1 order of magnitude smaller than the nanometer. A nanometer would be to the -9th. This is to the -10th. So this would be 0.1 nanometer. There we are. So 0.1 nanometer. That's a fast-moving electron. I also want to point out we have a unit for this. It's called the angstrom. So 1 angstrom has a little circle at the very top of it. It's going to be 1 times 10 to the -10. That's actually about the size of an atom. So if we can slow it down to be 1/100th the speed of light, give or take, we've actually still got the electron being the size of an entire atom in terms of where it's blurred out. And remember, wavelength, when we were talking about light, we said the photon is actually spread out over space. So what we're saying is that our electron actually has spread out to become the size of the entire atom. That's kind of a funky outcome. Now, if we take an alpha particle, here we're getting something that's a lot more heavy. This is about 4 orders of magnitude more heavy. 4 orders of magnitude means 4 zeros after it, so it's 10,000 times bigger, or at least 10,000 times heavier. When it's that much heavier, even moving faster than that, the wavelength is still minuscule. This is well below what we'd ever be able to detect or probably even care about in terms of the scales that we're talking about, even with an atom. And at the macro scale where we live, we're not going to be noticing that. Now, let's just see what happens with a couple of things that are observable size. Notice our masses. If we get them to be fairly large, we do expect the wavelength to be pretty large. To be pretty small. If we have really fast velocities, Big number down here, small number there. So if I take a 1 gram mass and I'm pushing it at 1 centimeter per second, this is the wavelength that we're dealing with in terms of meters. Now, I said that this was going to be something that was perceivable, but look at this. This is 19 orders of magnitude smaller. You're not going to see that. So while a 1 gram mass, what's 1 gram look like? Remember, 1 milliliter of water weighs a gram. So we're talking about a sugar cube size of water. Something about that mass, or about the weight of 3 aspirins. That's the kind of wavelength you're talking about. Are we going to perceive that or care about it? Absolutely not. And that's why we never detected it until reasonably recently in mankind's history. If we look at a baseball, and let's just say that it's somebody who's throwing it faster than I probably can, 25 meters per second. It weighs 142 grams. Wavelength is even smaller. If we take the entire Earth, Earth is going to have a wavelength. This is the mass of Earth. Very large number down here. It's moving at a pretty good speed, so another large number down here. Really big numbers on the bottom mean really, really tiny wavelengths. It can be helpful to draw arrows next to an equation like this in order to spot what the outcomes would be. And you can see here that the wavelength of Earth is negligible. So that's going to be our deBroglie wavelength in a nutshell. In a separate video, we'll take a look at exactly what that means for what's happening down at the scale of the atom.